we're thinking about how we can graphically represent the movement of a traveling wave. It's simpler to just imagine a pulse rather than a wave that continues and spreads out for over a great distance. So just imagine instead of, think of these as pulses on a string. Instead of continually vibrating the string, which will make a long series of pulses that look like this, imagine just shaking the string once. And so all we get is one pulse shaped like this. And then we'll imagine that this the wave speed on this particular string is 10 centimeters per second, and this pulse, let's say, is moving in the positive direction. There are two kinds of graphs that we can make. One is the so-called snapshot graph, and a snapshot means, like the name implies, it's a picture of the wave shape at one moment in time, just as an actual snapshot is a picture of things at one moment in time. So in each snapshot graph, you have to identify a time, a particular time when that snapshot shows the way the system looks. For example, at time 0, here's our pulse right here, 2 centimeters wide and extending from -1 to -3 centimeters. Now, since the speed is 10 centimeters per second, moves 10 centimeters in 1 second, it will move 1 centimeter in 1/10 of a second. So in that sense, it makes easy, it's going to be easy if we think about taking a snapshot every 1/10 of a second, because in every 1/10 of a second, the pulse moves 1 centimeter. So for example, here's a snapshot 1/10 of a second after this one. So everything has moved in the positive direction 1 centimeter. But since the pulse is moving left to right, this is the front edge, this is the back edge, and so the front has moved from -1 centimeter to 0. And then the back edge has moved from -3 to -2. And then wait another 1/10 of a second, take another snapshot. So that's a snapshot at time 0.2 seconds. And again, everything has moved 1 centimeter. The front edge of the pulse has moved from 0 to 1, and the back edge of the pulse has moved from -2 to -1 centimeter. Keep going. Another 1/10 of a second after this. That is 3/10 of a second after the start. Then the front edge has moved from 1 to 2, and the back edge has moved from -1 to 0. And then I've got snapshots here. This one is 1/10 of a second after this one, and this snapshot shows the way things are 1/10 of a second after this one. Or to put it another way, just compare the very first snapshot in this series with the last snapshot. They're 5/10 of a second apart. In each 1/10 of a second, the pulse moves 1 centimeter. So in 5/10 of a second, the pulse should have moved 5 centimeters. And we see that. At this time, the front edge of the pulse is at -1, and then 5/10 of a second later, the front edge of the pulse is at +4, 5 centimeters away from where it was here. In those 5/10 of a second, this front edge of the pulse moved 5 centimeters from -1 to +4. And likewise, the back end of the pulse moved 5 centimeters in those 5/10 of a second. It starts out at -3, and then 5/10 of a second later, it's at +2, 0.5 centimeters in the positive direction away from -3 centimeters where things started, where the tail end started. Okay, that's That's one kind of graph. The other kind of graph is a so-called history graph. And instead of looking at how a whole bunch of different points on the string are displaced away from equilibrium at one point in time, which is really what a snapshot does, right? Here at this time, at the 0.03 second mark, this bit of string here at 1.5 centimeters is at its maximum displacement on the negative side, and this little bit of string here at 0.5 seconds is at its maximum displacement on the positive side. So instead of a snapshot, we have a history graph which tells us what's happening to just one location at different times. Or to put it another way, it shows the displacement of one piece of the string as a function of time. Or it shows how one little bit of mass that's in the path of the wave is displaced at different times. Displacement as a function of time. So in any history graph, you have to specify a particular location, and you're thinking about what's happening at that particular location as time goes by. So let's try one location for a history graph, x equal 0. So, and being a history graph, it's showing displacement versus time as opposed to displacement versus location here on the snapshot. So time on the horizontal axis. And then let's see what's happening to x equals 0. At time 0, nothing has happened yet to this little bit of string at x equals 0 because the pulse is still to the left of it. At 1/10 of a second, the front of the pulse has just arrived. So things are starting to happen. In that second 1/10 of a second between this time and this time, this part of the pulse has passed through the x equals 0 point. So that is, let's say, here's the 0.1 second mark, that's when things start happening. And at the 0.2 second mark, the front half of the pulse has finished moving through the x equals 0 point. So what happens when this front edge of the pulse passes through? First it pulls down, pulls that little mass at x equals 0 down, and then pulls it back up to equilibrium. And then at 3/10 of a second, the back half, between 2/10 of a second and 3/10 of a second, the back half of the pulse has passed through the x equals 0 point, so that at 3/10 of a second, the very back edge of the pulse is just leaving the x equals 0 point. And during that 1/10 of a second between this and this piece of the pulse has been passing through x equals 0, and what does it do to the mass at x equals 0? First pulls it up, and then pulls it back down to equilibrium. So that's the behavior of any point that sees this, any little bit of mass that sees that pulse passing by. And of course, any other point on the string will experience exactly the same kind of things. First, it'll be pulled down, then pulled to negative displacements, then it'll be pulled to positive displacements. Because for every point on the string, this being the front edge of the pulse, this will pull a little bit of mass first, and then the back half of the pulse will pull on the little bit of mass last. The history graph for every point anywhere along the string will have that same shape, just happening at different times. So, for example, let's say a history graph of what's happening at not x equals 0 centimeters, but x equal 2 centimeters. So at 3/10 of a second, that's when the front edge of the pulse arrives at the little bit of string mass at the 2 centimeter mark. Before this time, the pulse was farther in the negative direction, away from the 2 centimeter point, just approaching, getting closer to the 2 centimeter point, and the front edge arrives at 3/10 of a second. So nothing happens until 3/10 of a second. And then things happen in the same order as they did to the x equals 0 point. They just happen later because x equal 2 is a little farther downstream. First, in 1/10 of a second, the pulse gets pulled down, then back to equilibrium, then gets pulled up and back to equilibrium in the following 1/10 of a second. So at 5/10 of a second, the back edge of the pulse, the last bit of the pulse, is just leaving the x equal 2 point, moving that way. And between 0.3 and 0.5 seconds, this whole pulse passed through the x equal 2 centimeter point, and this being the front, this acts on the mass, the little bit of mass at x equal 2 first, pulling it in the negative direction, then back to equilibrium, and then this being the back half acts on the little bit of mass at x equal 2 last, pulling it in the positive direction and then back to equilibrium. Just one more to illustrate this. Let's think about a point on the negative side of x equals 0. So let's say x equal to minus 3 centimeters. And let's see what the history looks like in that case. So here's displacement versus time. And notice I've extended the range into negative times because what do we see here? At time 0, the back edge of the pulse is at x equal minus 3. So at time 0, the back edge of the pulse is just about to leave, which means the front edge of the pulse arrived at an earlier time than the time when this snapshot was taken. The front edge of the pulse, the whole pulse is moving left to right. At earlier times, this pulse was farther to the left. So at earlier times, the front edge of the pulse was here. Earlier times than this time equal 0. So right away, what do we know? We know that at time 0, the pulse is just finishing passing through the x equal minus 3 point, and after that it's moving farther and farther away from x equals 0, so nothing happens at positive times. Everything that happens to the x equal minus 3 point happened before time 0, before you turned on the stopwatch. So minus 0.3 minus 0.2 minus 0.1 seconds. So here's the bottom edge of the pulse is there, at time 0, this pulse is moving 1 centimeter in 1/10 of a second. So 2/10 of a second earlier than this pulse was 2 centimeters to the left. So in other words, 2/10 of a second before this, at the time negative 0.2, the front edge of the pulse was 2 centimeters to the left of this. In other words, it was at -3. At 2/10 of a second before this, the front edge was just arriving at x equal -3. And so that's what the front half does, and then this is what the back half does. Right. At the earliest time, this is the earliest time when something starts to happen to the mass at x equals 0. And then this is the last moment when anything happens to the little bit of mass at x equals 0. And like I said before, same shape as the history graph of any other point, it's just happening at different times. One thing to notice here, the shape of the history graph is flipped around. The left side of the snapshot becomes the right side of the history graph. Right? The left side of a snapshot shape becomes the right side of the shape of the pattern that you see in the history, and the right part of the shape you see in the snapshot becomes the leftmost part of the pattern that you see in the history graph, because it's moving left to right. So this is the front half, meaning this is the part that arrives first, and that's the way it will always work for any wave or any pulse moving in the positive direction. If the pulse is moving in the negative direction, then in that case, the shape of the snapshot and the shape of the history turn out to be exactly the same. Let's see how that works. So in this case, we'll draw just one snapshot, and then based on our knowledge about the wave velocity, we'll be able to construct the history. So, excuse me, just for some variety, we'll do it the other way around. We'll start with knowledge of the wave velocity and a history graph, and from that we'll get a snapshot. Here, of course, it was the other way around. We started with snapshots and then deduced some history from that. Now we'll start with history. Let's say this is the history of the x equals 0 point. And let's say now this time the wave is moving right to left. Now it's got a negative velocity, but still the speed is the same as before, just to keep things simple, 10 meters per second, or 10 centimeters per second, or 1 centimeter per 10th of a second in the negative direction. So let's for a little variety here, let's say we have a different kind of shape here. History, so that's a graph of displacement versus time. And let's say things don't happen to the little bit of mass at x equals 0 until the 0.5 second time. And then things will be happening to that point for 0.3 of a second. Say the first thing is that it gets pulled to negative displacements and then pulled back to equilibrium, and then pulled up to a positive displacement, and then a constant displacement, and then very rapidly pulled back to equilibrium. So rapidly that on this time scale it just looks like practically a vertical line. Okay, so that's what happens to the x equals 0 point. At 0.5 seconds it starts to be pulled negative, and then from 0.6 to 0.7 seconds it's being pulled positive, and then for this 1/10 of a second it stays at a constant positive displacement, then suddenly pulled back down to equilibrium. Okay, what kind of a snapshot would correspond to this? And remember, for a snapshot, you must always specify the time at which the snapshot was taken. So let's say a snapshot at 0.3 of a second. And of course, a snapshot tells us shows us the shape of the wave pattern at some particular moment in time. Okay, at 0.3 of a second, well, we know at 0.5 of a second, the pulse had arrived at the x equals 0 point. So 0.2 of a second before that, it must have been 2 centimeters away from the x equals 0 point, because this is traveling at a speed of 1 centimeter per 1/10 of a second. So this time, the front edge of the pulse is 2 centimeters away. And since the pulse is moving right to left, and since this is the stuff that happens to the mass at x equals 0 at the earliest times, this is done to that mass at x equals 0 by the front part. So the front part must look like that. And this front part has to be 1 centimeter wide, because according to the history here, it takes 1/10 of a second for that negative displacement part to move all the way through the x equals 0 point. So, and this thing travels at 1 centimeter per 1/10 of a second. And so if this is 1/10 of a second long, then it must have been 1/10 of a second wide. And likewise for each 1/10 of a second here. In each 1/10 of a second, in each 1/10 of a second, there will be 1 centimeter of this pulse that will pass by any particular point. So this is what happens to the mass at x equals 0 in a 1/10 of a second. So this must have been 1 centimeter wide. And likewise, this must have been 1 centimeter wide. So it must look like that. And now you can see that as opposed to the situation when the pulse was moving left to right, now when the pulse is moving right to left, that means this is the front edge of the pulse, so this acts upon any little bit of mass first. So being pulled down to negative displacements has to happen first. It's what happens at the earliest times. And then this stuff happens later because this is the back 2/3 of the pulse. So the kind of things that this piece of the pulse does happen at later times. So everything else is just another variation on this, either figuring out what the history looks like if you know what snapshot pictures look like, or vice versa, figuring out what snapshot pictures look like if you know the history. Or you might be given both a snapshot and a history, and you have to figure out the velocity from that. And there are questions of that are similar to all of those three situations in the assignment. It might sound kind of complicated, but in the assignment I've broken it down into simpler questions, and that should help a bit.